Today the talk will be given by Ramiro Robles. Ramiro is now here for a few years, for more than 4 to 5 years. He's a research associate, and he's holding a telecommunication engineering degree from University of Mexico, 2001, and his PhD from University of Leeds in the UK. And currently he's working on in the Excel Scott project. And before this, he has contributed in several FCT and FP7 EU projects related to MIMO, RFID, Internet of Things, to name a few. So today he will be talking about cooperative and retransmission diversity for real-time multiple antenna communications. The talk will be around 35 to 40 minutes. So, yeah.
Okay, thank you, Patrick. So, well, thank you for coming. I didn't realize it was Easter time, so I didn't expect as many attending today. So, sorry also for the title. I realized that it was quite long. I'll try to make it not as boring. So, the presentation is more about what we call real-time wireless communication. So, I know that I'm here with real-time people, some of you, some mainly wireless. So basically in wireless, what we call real-time, it's very basic, because wireless is an unreliable propagation media. So what we call real-time is really ultra-low latency, right? Very small latency, because wireless is not reliable, so we cannot ensure the deliverable of data in a specific amount of time. As I said, real time is we'll analyze it only ultra low latency, and we are targeting two tools that we find that they are attractive for achieving this, right? Especially in the context of 5G. So, this also serves as a convergence between what we have here in the lab, real-time team with the wireless team. So what we have seen today is that there's a lot of funding, grants, and research effort in this convergence. Okay, so in the past we had this wireless networking, nobody cared about real-time because it was unreliable, and we had the real-time community, which was more in the computing aspect. Okay. So just to make it quick, I know that the sandwich session at the end is the most important part, so I'll try to make it as quick and understandable as possible. So wireless communication, the history, we started obviously with radio, AM, FM in the 1920s, 1970s, radar, all the identification, frame and identification. Obviously, the first generation of cellular system was around 1980s. It was analog, voice-oriented. It was AM, FM, as I said, analog communication. Then came the second generation of cellular, which was voice, but this time was digital, such as CDMA or TDMA, right, in the 1990s. Then the third generation, which started around the 2000s. Reality in market was 2007, but in the 2000s was already defined the third generation, which was the convergence of voice, data, and all digital, right? So it was internet on your phone, but it was mainly human-oriented, okay? This was the third generation cellular systems. And more or less at the same time, there was another development. There has been always different paths for wireless. This is only a very brief overview. So packet wireless, we have obviously RFID, Bluetooth, wireless sensor networks. Wireless sensor networks have been a lot of time there in the research arena. Obviously, this evolved of what we now know as IoT, Internet of Things, ultra wideband, then industrial Internet of Things, machine to machine. So all these concepts have evolved at the same time more or less in parallel to the cellular generations. Then we had the 4th generation, which was just the evolution of 3G. So it was increase of capacity, a different technology, more or less in 2010. And obviously now, I think what the purpose of this is just to show that there is a convergence here, right? So basically we have Internet of Things, machine to machine, based on legacy wireless sensor networks, which only work in the local area, in the home. And we have cellular technology that works in the urban area, right? So obviously it makes sense to think that we can create a technology that can converge or put the two together in what is called 5G, right? It's a commercial term. We have said here before that it's just a commercial term. It's not completely defined, but the idea is to have what if we can design a cellular transmission system where you can connect all your objects that we usually put in a wireless sensor network, but at the level of the city. So this is more or less the idea of 5G. Obviously, there are a lot of requirements. If you have industrial Internet of Things, then you need ultra low latency. The cellular communications were not designed to handle ultra low latency because they were designed for human users. So we have to modify the cellular transmission technology to fit with the new requirements. And that's more or less, in a broad view, the idea of 5G, okay? Obviously, for us researchers, it's just an excuse to have more funding and keep on going with our research topics, right? So this is just a summary. So what is 5G? 5G is the next generation of wireless cellular infrastructure, all right? It's the convergence of cellular, wireless sensor, IoT, M2M, and CPS systems, okay? So basically, we have these 4 main requirements or main objectives of 5G, okay? So it's ultra low latency, right? Because if you have an industrial application with 5 milliseconds of response, that cannot be achieved with LTE or with 4G, right? Basically because in LTE you have 10 milliseconds frames, so you cannot achieve less than 10 milliseconds delay or latency in LTE. Now, we want dense objects because now in cellular you had probably 20 users per base station, and now with the IoT you're going to have hundreds or even thousands of objects connected to the same base station. So the system was not designed to handle that amount of objects connected, right? So in that sense, higher capacity, yes, we need higher capacity, but it's not in the sense that we understood before in 3G, 4G, that we are going to get, instead of 100 megabits per second, we are going to get 1 gigabit per second. Higher capacity is more in the sense of how many services we are going to support, right? So it's not only that we are going to get now 1 gigabit per second, but we are going to get how many objects, how many services we're going to have, industrial applications with real-time requirements, voice, data, etc. Right? So it's a wider sense of capacity. So in that sense, adaptivity, which is more or less what this presentation is about, it's going to be a huge thing in 5G. Adaptivity means that we have intelligent systems that detect the radio conditions and adapt to those conditions. Okay. Well, adaptivity comes with this problem of wireless networks that are unreliable. So we need to adapt, all right? So when the channel is down, we need to adapt our transmission resources to counteract that loss of reliability of the channel. Just to deal more with motivations, obviously this is what we write in all the papers, right? So it's like 50 billion devices will be connected to the cloud in 5-10 years time. Industrial automation, end-to-end, and cyber physical systems. This is what we mentioned. Cellular technologies cannot cope with large numbers of objects. 3G, 4G solutions were designed for humans, not for machines, right? And wireless sensor networks cannot achieve cellular coverage service for industrial IoT, right? It is more or less what we said, and is more or less displayed here. So this is a chart of data rate versus range. So we have the different technologies. This is, for example, these are the technologies that we are using for IoT at the moment, and the range is just from 10 to 100 meters, right? So So the idea of 5G is to do this IoT, but at a bigger scale, right? So and with a single standard. So that changes a lot of things in the market. So that means the industries can be connected to each other in the same city. So you don't have to deploy a wireless sensor network on one and another technology in another building. So it's going to be only one standard. Right? Well, that's the idea, all right? So I just want to show that, well, for us that we work in wireless, there's a gap here, right? There's obviously a technology that can handle IoT, but at the urban level. So that's the gap that we're trying to fill in, right? And so now, why wireless has problems with real-time traffic? Basically because there's an infinite number of reflections, diffraction, obstacles, etc. Whenever you transmit wireless, the signal goes everywhere, reflects everywhere, and it creates this complex propagation setting that is very difficult to predict, right? So if you want to do deterministic wireless transmission, then basically you have to create, for example, in this room, you have to create a grid and solve the equations of Maxwell for every object moving and reflecting. So that takes a lot of time, right? So it's possible, right? But it's computationally impossible to make wireless deterministic, right? So that's why the wireless channel looks like this. It's just up and down, fading in time, in frequency. So every aspect that you want to analyze of a wireless network is this changing complex statistical process, right, that we have to consider, right? So obviously, I'm not going to go into the detail, but there's reflections, there's shadowing, fast fading, small scale fading, large scale fading that have to be accounted, right? So that's why when we transmit something, it's not going to get there the first time, right? Most of the time. So we have to retransmit, carry on until it's correctly delivered. And that's the problem with achieving real time in wireless network. So obviously, what I want to present is how we can achieve that, or nearly achieve that, trying to counteract these problems of wireless networks. So one of those is spatial diversity. And so it's another name of multiple antennas. Well, the idea of multiple antennas is very simple, right? So if you have a multiple antenna, for example here, we have two antennas and one of them has a low channel or a fading, then the other one might not have the fading, right? So you are just adding diversity in your system. So the more antennas you can have more chances of recovering your signal that you have transmitted. And obviously there are many different types of multiple antennas with signal processing. There is a huge amount of work there, right? So minor systems will be the base for 5G solutions. They have been for 3G and 4G, but they were really minor implementations, really. It's not the full potential of minor. I shouldn't put maths in presentations, but I just want to show closely briefly what it is. When this is the MIMO channel, when you have a MIMO, you describe it with a matrix, and we can decompose it. We call it singular value decomposition. We have n transmit antennas, n receive antennas. H is the MIMO channel, m times n. Tx is the beamforming matrix. U is the Rx beamforming matrix. And basically what this means is that we can decompose any MIMO channel, we can decompose it in these two matrices and the one in the middle, which is a diagonal matrix, which means, what this means is that any MIMO channel represents parallel streams of information, right? So this is like a linear system of equations, and we just solve the system for different streams. So for example, if we have an antenna of 2 times 2, that means that we can send at least 2 times the information that with one antenna, right? So that's the capacity of MIMO. It's just the minimum of the transmit and the receive antennas. So if you have, yes?
Sorry. So here we assume the channel or the link of the different antennas is non-correlated.
Yes, of course.
Okay. So what if it's correlated?
That's one part of the of the topics here. Well, it's not shown here. This is just the ideal case, all right? When it's correlation, the quality of, well, basically what it happens to your diagonal matrix is that sometimes you lose a term, right? Or the value of the diagonal matrix reduces, so the quality of the information is reduced. This is, it's a question that I was going to. So one of the main aspects that affects antennas is the correlation. So basically, if you have antennas that are very closely located, there is a lot of correlation, right? So the idea, that's why in the base stations you see they try to put antennas as far as each other in order to reduce what we call as space correlation. Right? So, well, this is spatial diversity. There is another type of diversity that we call cooperative and retransmission diversity. So, in this type of diversity, we can use multiple antennas, but basically we assume that terminals cooperate with each other, right? So, let's say that this terminal sends its transmissions here. It fails to reach the base station, but it doesn't fail going to other terminals. So the other terminals can decode the signal and relay it instead of the original terminal, right? So if you see, these terminals are cooperating with this, right? And basically they are acting as a multiple antenna, right? But just distributed in the network. So this is what we call cooperative diversity, right? So it's not only that this terminal helps this to transmit the signal. What we are doing is we actually want to do a multiple antenna, virtual multiple antenna, with all the terminals in the network. All right. So it's like if you have all your terminals here, and my terminal cannot reach the base station, you form a coalition, we call it, and then you help my signal to reach the base station. So obviously this cooperative diversity has different advantages, disadvantages. Obviously, there is no spatial correlation like in MIMO because the terminals are located far from each other, but it has to take place in different time slots. Okay, so we need one time slot for the original transmission, and then another time slot for the relaying of the signal. Okay, so it's cooperation, but it takes resources in time. Okay. So if you compare it to the previous, we had only multiple antennas and you can receive simultaneously in the same time slot, right? In cooperative diversity, you have this virtual antenna made by your terminals, but it has to take different time slots, okay? So, I mean, this means that we need a process to say, please cooperate with these terminals and relay the signal to the base station. And we can actually do this retransmission scheme. This is what we call retransmission diversity, right? So the relaying terminals keep retransmitting until the signal is correctly received by the base station, okay? So what is important of this is that with cooperative diversity, we achieve diversity like if it's a multiple antenna, but at the same time we have some protocol in the MAC, right, for retransmission of the signal. So this is important for real time, right? Because once you don't, you send a signal and it's not correctly received, and you ask for cooperation, the others can keep retransmitting until the signal is correctly received, right? So this gives us a framework for real time analysis. So basically, we only have to, what we are doing here is just doing actually this protocol, right? Assuming that there's a terminal that tries to send a signal to the base station, it cannot reach, and then all the others come to help the terminal. And they keep retransmitting until the signal is correctly received by the base station. So if you see this closely, it's not, this is also a mechanism for a reduction of interference or attacks, okay, because you can keep retransmitting the signal until you are sure that it can be correctly received by the base station. So that's basically the two types of retransmissions that we are combining. It's a very basic combination. There's a lot of works in each one of these diversities. So what we are doing here is just coupling them together and show or try to calculate how long it takes for a packet to be correctly received by the base station in many different circumstances, right? With fading, or maybe there's an obstacle, or maybe they are moving too fast, all right? And that's the idea for us to analyze the delay or ultra-low latency of wireless networks. Obviously, we want to, in the future, we want to put different technologies. There are many variations of cooperative and spatial diversity that we can put into this framework. But the importance of what we're trying to do today is to have the framework to analyze this aspect, how long it takes for a signal to be correctly received by the base station. Consider that the wireless is changing, that the first transmissions can be incorrect, and we need to recover the information. So this is also another aspect that we call this cross-layer design, because we are combining aspects of the physical layer of the multiple antenna with the MAC, which are basically retransmissions. Okay? Obviously, in real life, in a protocol, these retransmissions cannot occur immediately after one another, right? Okay, so you have to wait for the delay to go to the base station to process the signal and request the retransmissions. Okay, so this is just an ideal setting that we see that the next time slot you receive the next retransmission. Okay. Okay. Well, this is just a comparison. We have space diversity with cooperative and retransmission diversity. Is the two types of solutions that I showed you before. So space diversity doesn't have temporal correlation, but cooperative and retransmission diversity have temporal correlation. Maybe I forgot to say that. So in MIMO, you have the problem of correlation because the antennas are closely located to each other. So you have the signal can be correlated between antennas. And in cooperative diversity, you have the problem of correlation between time slots, okay, between retransmissions. Okay, so this work, we are trying to put these two aspects that are the main issues of these two types of diversity. So when we compare, obviously, we have cooperative retransmission diversity suffer from temporal correlation, but they suffer from selection issues. What we said that you have to put the protocol and request the retransmission from the relays. That doesn't happen in space diversity. But cooperative diversity has no space correlation, as I said, because the terminals are located far from each other, and it doesn't have implementation complexity because basically you are simulating a multiple antenna system without having the multiple antenna system. Okay? What I mean is that you have kind of a multiple antenna systems created by the relays, but without implementing the MIMO system, right? So that's the trade-off, right? So is the trade-off complexity, correlation in some cases, selection issues in other cases, and that's the trade-off that we will have between the two types of diversity, right? Now delay, here is more or less how we calculate delay. We have this tool that's, I don't know how in real time data you evaluate the delay or latency, but here we, at least in networking, in these type of systems, we use what we call the MG1Q with vacations, right? So M means that it's Markov arrival because we consider the traffic arrival, right? Maybe in real time, I don't know, you don't consider the traffic arrival distribution, but in networking we do. I don't know why, right? But Markov, it just makes the things more difficult, but it's Markov arrival, it's just a Poisson statistical process. So we simulate that we are receiving packets with with a different rate. Okay, G is a general distribution. Is what we say that it takes a random amount of time slots to transmit the information. That's what the G means, is because it doesn't have a distribution. And one is one server. Obviously, we can put more servers, but that's another topic, right? So basically, what I want to emphasize here is that in wireless networks we have all you can see is average delay calculation. That's what all the people do. And for real-time evaluation, what we propose is a different approach, because the average is it can be a very fake or very it doesn't give the information of the system. Maybe you have an average delay time of 10 milliseconds, but it has variations of 10 milliseconds. So you can have packets that take 20 milliseconds or 5 milliseconds. So it's that variations of delay that are important for real time. We propose that in wireless networks, real time is not only the average delay, it's just the full statistics of delay. And I'll show you why. So this is the idea of delay calculation. We have packets arriving. This is the queue. It looks it's a very simple drawing. We have packets. Packet 1 starts to be transmitted. It's incorrectly received by the base station. It needs retransmission. Another retransmission. It's again incorrect. You receive another packet. So this is the problem. So this packet number 2 has to wait for packet number 1 to be transmitted. So this is what we call queuing delay, right? So packet 1 has been correctly received now in the third time slot. Packet 2 has waited already 2 time slots. Okay. Now packet 2 can start to be transmitted. It's correctly transmitted in the first time slot, but we receive packet number 3, who has to wait 1 time slot. Then packet 3 can be transmitted, is incorrect transmitted, and then the second attempt is correctly transmitted. So this is how we calculate the delay, right? So we consider the queuing and the service delay. Probably in real time is different because well, at least what I have seen, I have not seen that you consider this queuing delay, right? But it's a different setting, right? Here we have an unreliable channel, and we have to wait for the packet to be transmitted by the network, right? So, this is the typical calculation. So it's just we do the average of all the receivable times. When you receive the packets, you have receivable time. You have to wait for the other packet to be served, and then the service time for you to be served. So, well, this is just the calculations. I won't go through it very detailed. So what we do is that the delay is composed by the queuing delay and the service delay, and that's basic, right? And because we have a wireless channel, this is very difficult to calculate. You have to go through statistics, so we have to do the PDF analysis, central moments. We do Fourier transform analysis to get the characteristic function. We do this because it's easier going this way than the other way, right? So all you have to know is that we are trying to get a framework to calculate this latency of wireless transmission, and that we can use in the future for 5G. Because as I said, most of the works are focused on average delay estimation, but for real time we need the full statistics, and I'm going to show you what I mean with that. All right. So we have some preliminary simulation results. It's the same as this cooperative network. So we have terminals transmitting to the base station. If the signal doesn't reach the base station, others come to help the terminal. Only terminals that have the correct version of the signal relay the same signal to the base station, and this takes different time slots, right? For example, here terminal 1 transmitted, it was incorrect. 3 and 4 help in the second time slot, it's incorrect. Again, they help in the third time slot, it's incorrect, and they keep retransmitting until it is correctly received. Okay, and the same happens with. So we assume this frame structure, and we want to see what is the performance in terms of delay and statistics of delay. Right. So I don't know if you can see very well, right? So what we want to do is what we call this cumulative distribution function, right? So it's just the probability that the delay is below a given value. Okay. So we're showing here a service delay, which is simple, right? Because it's just how many time slots it takes a packet to be transmitted. So what it means is that, for example, for these results, it's the probability that the delay is lower than 6 is equal to 0.3, right? And what I want to show here is that this is the best we can do in wireless, because we cannot assure you with 100% accuracy that the delay is going to be 5 milliseconds or 10 milliseconds. All I can do is to say the delay is going to be below 10 milliseconds with probability equal to 0.4, 0.5, 0.9, all right? And here we just change the parameters. Here we are showing different antennas. Obviously, when we increase the number of antennas, we have more reliability. So the probability is high to have lower delays. And if we include some space correlation or other impairments, this probability goes down. Right? Yes.
Okay. When you say increasing antennas, it's on the base station or all the nodes in the system?
No, just the base station. Yeah.
And second is usually along with the average delay, what they usually give is the standard deviation to capture that particular aspect.
Yes.
So are we saying this probabilistic value is the kind of equivalent of that?
Yes. Here I'm trying to be more ambitious, right? Because in reality, the average and the standard deviation is what we call jitter. It's just two metrics, and if we calculate the full statistics, you get all the performance, right? So actually you can go and say, I have a probability of having delay below 30 milliseconds with a probability of 0.9, and I think that's more complete than just to have average and standard deviation. But yes, standard deviation goes in that sense, right, to provide more information about how is the delay in wireless networks. And here, multiple antennas. Yes, we combine spatial diversity with cooperative diversity, but we put only antennas at the base station. But it can be also in the relay nodes. I mean, it's just to change a little bit the simulation parameters. And this is just generic. This could be also a vehicle platonic, right? It could be, I mean, these terminals can be just aligned in different cars, and the different cars relay the information of each other to the destination, which can be a base station, or it can be another of the terminals in the platoon, right? So this is just a very generic setting, right? Yes.
So when you say that your relayers fail to deliver the message,
Yeah.
what does that mean exactly? Is there due to some interference? Is it due to contention? What can be the issue?
We can put almost anything, right? It can be.
But
it
the
can
MAC
be
is not slot based, is it? The MAC, is it slot based?
Yes, it's slot based.
slot
Yes.
So in principle there shouldn't be contention, right?
We have done this in contention base as well. I mean, this is just an example. Here we have just one terminal transmitting in the time slot. I mean, it's a very simple calculation, but we have done contention as well. So, but it's more complex, right? I mean, As I said, in the past we were only focused on average delay derivation, right? And now we are trying to do this more high-level calculation of delay, so that it can be said, well, I can achieve real-time communications in these settings with this probability, right? But we started with this simple, but we have done contention or interference. Basically, here, what I was saying is that this carry-on retransmitting, it can be due to contention or interference that doesn't allow you to get the information. In this particular case, we are just with signal-to-noise radio, right? So the signal is not strong enough to be correctly decoded, and then after the fourth retransmission, you combine all the retransmissions or all the signals, you do minor processings, and you get the signal quality that you want. This is a very complex field because many other people use different metrics, right? Signal-to-noise radio or block error rates. So there are many different metrics to decide when to stop retransmission or when to request the new retransmission. Here we use signal-to-noise and interference radio because it's more simple and we can get closed form expressions that allow us to do this, right? To derive the full statistics. It can be shown in many different ways. Here I showed you the cumulative distribution function because it makes sense to show that there's a probability to get the delay below this under these circumstances, right? Yeah. Okay, thank you. Yeah. So well, that's it. Obviously. The idea is to do these delay calculations with different types of physical layer, MAC, even if we can do with the conventional protocols like 15.4 or .11, right? And to do the evaluation, can we get real-time traffic or not? Right? Okay, thanks.
Thank you. We have a couple of questions.
It's related to this probabilistic delay, worst case delay. Would you do something similar to what people in worst case execution time community doing when they are using the extreme value theory to make the tail reconstruction of the probability distribution and then consider those rare events to make this worst case delay calculation? Or you would expect that this is going to be so pessimistic that it doesn't make sense to do it? Like, it will become useless. What would you expect?
I believe it all depends on the complexity, right? Because here we have chosen this setting because it's simple to derive these full statistics, right? But when the network becomes more complex, maybe we'll have to do something. Approximation, tail distribution, the worst case scenario in the network to evaluate the real time. So I think it depends. It depends on the complexity of the situation. And here, this is very simple, but in wireless network you have a layer of optimization of resources, and you have to put targets to that optimization. And if it's real-time network, now the target is going to be the delay of each stream of traffic, so that is going to complicate things, and probably we cannot do this full statistic analysis there, and we have to come up with what you said, some other metric that is more relevant for that optimization, because we are talking about, this is a very simple setting, we are talking about 5G, and we have a cell on 5G. I think it's going to be like 1,000 objects trying to connect to your base station rather than just 2 or 3 that we use here, right? So yes, it makes sense what you said. It depends on the complexity, and we will see when it comes to the point that we put, instead of 10 terminals, 1,000 terminals. Maybe we cannot do this analysis anymore, and we have to do this simple analysis. Yes, Lucas.
Yes, for that NG1Q model,
Yes.
what's the state in your macro chain?
Pardon?
What's the state in this macro chain?
The state.
The state, yeah. in this Markov chain? I guess it's the number of packets in the queue.
Yes, it's a Markov chain, and you just assume that you have one or two packets arriving per unit of time, right?
So it's number of packets in the queue of sender, right?
Of the sender, yes.
Then basically you are calculating the queuing delay.
Yes, that's yes, is what we explained here. Yes.
Okay. So my question is it like you should calculate the transmission delay?
Yes. Well, actually, this is what
the queuing delay.
we are doing the two. So we are doing both. So that's why the MD1 queue with vacations covers the two aspects. So the M is the Markov arrival, and it's for the queuing delay, and G is the distribution of the service. So it's the transmission delay, basically. So is the service is how long it takes for the packet to be transmitted here, right? So that's why it's with vacations, because you have to wait till the system is available to transmit the next packet.
But the transmission should, transmission delay should also include the relay delay, right? You have a relay there.
Yes, it's accounted. It's accounted here. I mean, this is what I said at the beginning. I mean, this immediate retransmission is just idealistic, right? I mean, in reality, you don't transmit exactly in the next time slots. You have to wait for delay and the signal. So, but it's you can assume that this happens in 2 time slots later, right? But this MD1, the MD1 queue with vacations covers queuing delay and service delay, and the service delay is basically the transmission, including the relays, because we are doing this relaying retransmission. So it's a random variable, because sometimes it takes 3 time slots to transmit your signal, or sometimes it takes 2, or sometimes it takes 10, and that's what we include in the calculation. And that's why it's a bit difficult to do an exact calculation, because you have queuing and the service delay, transmission delay. Okay.
Okay, let's thank the speaker again.
Okay.
Thank you.